Hello, this sequence is about building a project network and determining the critical path. So in this case, I'm going to go through sort of a presentation and verbally describe building the project network, and I will record subsequently an example where I do by hand work through a simple example to demonstrate the concepts that we introduce here. But this is the first overview on getting this done and should really lay the foundation for the example that follows. So the first thing we need to do when we're doing this sort of critical path approach is diagramming the network. We're providing a graphical example of what the network looks like. And it depicts the relationship between activities. So it says these ones are independent or these ones are linked through a precedence relationship, and it consists of nodes, which are circles, which represent activities, and arrows or arcs, which connect those nodes, and the arrows indicate a precedence relationships. They indicate that these things need to happen in sequence. There is another approach that I'm not going to focus on. It's not my preferred approach, but that you can see in various operations textbooks. That's called activity on arc, where the activities are actually the arrows, and I think the activity on node approach that we're going to cover here is more straightforward and easier to follow for students learning project management. And program evaluation and review technique, PERT, critical path methods are sort of what we're describing in this and subsequent videos to introduce the concepts in project management. So the first thing we need to understand is the concept of a precedence relationship, and the precedence relationships determines a sequence for undertaking activities. It says that one activity has to happen before another activity can start, and it is important to understand that because it helps. You know, we can't just throw all the activities in a bag. Well, we can if there's no precedence relationships, but we can't just throw all activities in a bag and just pull them out and do them whatever we want. We can't sort of prioritize longest tasks first, or a variety of priority tools to do that in absence of considering the precedence relationships. So if one thing has to finish before the next thing can start, we need to identify that because those tasks are then inextricably linked, and we need to take that into account. As I said, we're going to do the activity on node approach, which looks like this. So this is a very simple a very simple network. We have 3 tasks in order here, and this reflects that S has to be finished before T can start, and T has to be finished before U can start. So this is how we represent it in drawing a project network. We reflect those precedence relationships. S precedes T, which precedes U. And that's what we are articulating with a diagram that looks like that. And some other simple examples. In this case, both S and T have to be finished before U can start. And so we have to have both of them finished, regardless of how long they take individually, before we can begin U. That's reflected here. And in this example, S has to be finished before either T or U can start. Now, one can start before the other, but neither of them can start till this one is finished. And they may be different lengths, so they might finish at different times, but the arrow reflects the constraint of a precedence relationship. And we can have more complex ones. In this case, S precedes both U and V, and T precedes both U and V. And so neither of these can start before both of these are finished. If S finishes before T, it doesn't necessarily affect the start time for either of these, because both of these need to be finished before either of these can start. In this case, the one on the right, S precedes U and T precedes both U and V. So if T finishes before S finishes, U can't start, but V can. So we're just looking at different ways to articulate that concept of a precedence relationship, and this is how we diagram the network and reflect those precedence relationships. One last one here. S precedes both T and U, and T and U both precede V. And so T and U can't finish till S finishes, and T and U can't start till S finishes, sorry, and V can't start till both T and U finish. So if U is shorter than T, there will be what's called slack time in U, because it will likely finish before T does, but that doesn't allow V to start. So that gives you some flexibility within U, and we'll talk about that in a second. So let's talk again about the concepts here. We have the path, which is the sequence of activities between a project's start and finish, and we can have multiple paths. It is sort of a sequence of related activities between a project's start and finish. So we track the path of those arrows, and that becomes a path. And then the critical path, and there can be more than one critical path, and we'll look at that in the examples that we do later. The critical path is the sequence of activities between a project's start and finish that take the longest time to complete. And it's called the critical path because those tasks have to finish on time. They are critical to finishing that project on time. We have slack in non-critical paths, which give us some buffer or some flexibility in terms of timing without compromising the completion time of the project. But the critical path is that longest path, and the one that we need to make sure finishes on time so that the whole project finishes on time. So individual tasks or activities on the critical path need to be finished on time and are usually the focus of project managers. So here we have an example of a network diagram that shows the precedence relationship. I like to, and not everyone does this, but I like to have a start node, and what isn't on this one is a finish node that just helps you when you're calculating earliest start, earliest finish time, which we'll talk about in a minute. When we're doing our passes through the project, our forward pass and our backward pass, I think it just helps make it clearer in doing those determinations of the critical path. You don't have to, but as I said, I think they are helpful. So in this case, start comes before A and B, which means that A and B have no activities before them. C has A as a procedure. It can't start till A is finished. And D has both A and B. G can't begin till D is done and E is done. F and E can't start till C is done. And so we can see then the network of precedence relationships in this specific project. When we have that network diagram, the next step in the process is to perform a critical path analysis. And the critical path, as I said before, is the longest path through the network. The critical path is the shortest time in which a project can be completed. So if that means that if any activity on that critical path takes longer than is planned, it lengthens the project. So the longest path is the shortest completion time for the project, and it's called critical because otherwise the project can't get finished on time. Any delay in the critical path delays the project. And the way we determine the critical path, and there can be more than one critical path, as I said before, is that the critical path activities have no slack time. And slack time means there's some buffer. There's some ability to take a little bit longer if necessary, reallocate resources from there in order to keep the project on time. So how do we do that? We have four key concepts that we need to understand in forming that critical path. We have the earliest start time, which is the earliest at which an activity can start, assuming that all predecessors have been completed. So the earliest start is for an activity is the earliest period in the project we can start that, which means it is it depends on all the things that come before it. The earliest finished is the earliest time at which an activity can be finished. So the earliest start time gives us the earliest time that a project can start, and then the duration that that activity takes is added to the earliest start to give us the earliest finish. The latest start time is the latest time at which an activity can start so as not to delay the completion of the project. So the earliest start is the earliest time it can finish based on the things that come before it. The latest start is the latest it can start without making the project go longer, so it's more concerned with the tasks that come after, and we'll show you that in a second. And the latest finish time is the latest time that an activity can finish so as not to delay the entire project. And again, the difference between the latest start and the latest finish is the duration of that project, and of that individual activity. And so this becomes a little clearer when we work through an example. So we traditionally, sometimes you'll see this as a square. I usually draw it as a circle. You have this circle, which is the activity node. In the middle here, we have the activity name or symbol. Down here, we have the duration. Then usually in the upper left, we have the earliest start time. In the upper right, we have the earliest finish. The lower left, we have the latest start. And the lower right, we have the latest finish. So that just becomes the context for the information as we are drawing the network. I already talked about this. The earliest start time depends on preceding activity. So we look at those tasks that precede it, and we calculate the earliest finish time by adding the duration of that particular activity. On the latest start and the latest finish, in that case, we look at activities that follow them. So we calculate the latest start time, or determine the latest start time first, and then subtract the duration of the project to give us the latest start time. So we move through a project from left to right, from start to finish, to do earliest start, earliest finish, and then we move through the project from right to left, from finish to start, to do latest finish and latest start. And then we have slack, where we look at the difference between latest start and earliest start, or latest finish and earliest finish. And one check you can do for quality control in your project network is, if these two numbers aren't the same, you've made a mistake somewhere. The slack has got to be the same as the difference between latest start and latest finish and earliest finish, and it should be the same. And the slack is the difference between the earliest start and the latest start, and gives you a sense of how much buffer you have in that task. And so anything that's on the critical path has zero slack. Anything that is not on the critical path has slack. So as I said, we go from start to finish, what's called the forward pass, where we look at everything that comes, so if you have something that comes out of the start node, the earliest start time is 0 or whatever time the project starts, and we add the time and we get earliest finish, and we go through. It's easy, and it's easiest to see in an example. I'll do an example for you shortly. And if you have several tasks that have to be finished before the individual task that you're looking at can finish, the earliest start time is the largest of those earliest finish times that precede it, which means the earliest finish is the earliest that that activity can finish, and the subsequent tasks can't start till it's finished, so you take the biggest, earliest finish. And I'll show you that in an example shortly. The backward pass is once we've got earliest start and earliest finish worked through all the way through, we determine the latest finish on the critical path, and we subtract the task completion and we get latest start. And so we work backwards then, and then we take the latest finish of the task that, or the activity that follows it, and that becomes the latest start of the task that we're looking at. And it's often easier to understand in an example, but I need to introduce the concept here. If you have several tasks that come out of the task you're looking at, you take the smallest latest start time of those, because that is the latest start that task can start. So that's the latest, and the smallest one becomes the latest finish of the tasks that precede it. And again, I'll show you in an example shortly. We talked about slack time. Slack time is the difference between latest start and earliest start, or latest finish and earliest finish. And it is important that you double check. If those two numbers aren't the same, you've made an error in determining your project parameters. So here we have earliest start is 0 for that network we saw earlier because it comes out of the start node. Earliest finish is 2 because this takes 2. If we were to draw the network like we'll show, here we have latest finish is 2, latest start is 0, so we have no slack. 2 minus 2 is 0, 0 minus 0 is 0, so we have no slack, so it's on the critical path, and we would do that so on and so on through this set of activities. And you can pause the video here if you want to look at these, but I'd encourage you to take a look at the examples that I will show you subsequently. So again, I covered these things earlier in the introduction to project management, but I thought they were worth covering again. This approach is especially useful when scheduling and controlling large projects because it allows you to visually and explicitly address the sequence with which tasks occur. It's not mathematically complex. Once you've mastered earliest start, earliest finish, latest start, it's not mathematically difficult, and it becomes relatively straightforward. Looking at it visually provides some significant advantages, and the critical path and slack time analysis help to pinpoint activities that need to be closely watched. They highlight the activities that need special attention by a project manager. It also allows you to document who's responsible. It's applicable to a wide variety of projects. There's almost nothing that this can't work for as long as you can clearly define those activities. And it's useful not only in planning the project, but also in monitoring and benchmarking whether you're staying on track. So it's useful for that. And just limitations are that you have to be able to clearly define project activities and that they are separable from other activities in the project, so that you can explicitly diagram those networks. Precedence relationships must be specified and networked together, so they have to be definitive and clear. Time estimates need to be clear, although we'll talk about uncertainty in a later video. And you have to be confident that we don't have this euphoric optimism that a manager says, oh, I can get that done in this many days. It depends on accurate measures of activity times. Now, I said it's good to manage and it's good to pay attention to the activities on the critical path, but we have to remember the other activities matter as well. They may have slack, but they still need to get done in order to complete the project. So understanding how much slack is in them is important. So that gives you sort of a quick introduction into the concepts around developing a network diagram. The next video will show you a couple of examples where we build one from scratch based on the information of duration and precedence relationships. We determine the earliest start, earliest finish, latest start, the path from forward to start to finish, the path from finish to start, and look at, that allows us to develop the critical path. So that is the basics of doing a project network. There'll be a subsequent video on crashing or shortening a project. There'll be a subsequent video on ensuring that we have how we incorporate uncertainty in it, that will introduce those concepts. And there'll be 3 videos with explicit examples of building a network, crashing a network, and incorporating uncertainty so that it's clear as you work through problems in an operations management course in order to understand how to do these and to do the types of problems that you might be assigned. So thanks for your time, and stay tuned for more content.